T316 Advanced Networking. Session 1. SONET SDH, Classification of Communication Networks. Switched Communication Networks. Circuit switched networks, the telephone network, wavelength routing optical network, packet switched networks, IP network, MPLS networks, broadcast communication networks, examples, packet radio networks, satellite networks, packet switched networks, connection-oriented networks, MPLS, connectionless networks, IP circuit switched networks. In order for two users to communicate, a circuit or a connection has to be first established by the network. Specifically, the following three phases are involved: circuit establishment, data transfer, circuit disconnect. Connection-oriented packet-switched networks. Circuit switching is a good solution for voice, since it involves exchanging a relatively continuous flow of data. However, it is not a good solution for the transmission of bursty data. Connection-oriented packet-switched networks imitate circuit-switched network. In order for two users to communicate, a virtual circuit or a connection has to be first established by the network. The following three phases are involved: connection establishment, data transfer, and connection disconnect. Connectionless packet-switched networks. In an IP network, a user can send packets to a destination without having to set up a connection first, that is, without informing the network prior to transmitting them. This simplifies the network, as there is no need for a special signaling protocol. Routing an IP. The routing of a packet through the network is done on a hop-per-hop basis based on the destination IP address carried in the IP packet's header. Quality of service, QoS, in IP. Typically, an IP router does not offer QoS. It cannot distinguish packets belonging to different service classes based on their destination address. IP is almost ubiquitous. There has been a lot of interest in introducing QoS in the IP network, and MPLS seems to be one of the architectures of choice for introducing QoS. Examples of connections. Probably the oldest connection-oriented circuit-switched network is the plain old telephone system, POTS, known also as PSTN, Public Switched Telephone Network. Each subscriber is directly connected to a central office via a dedicated twisted pair line known as a local loop. Central offices are interconnected via time division multiplexing, TDM links, such as SONET/SDH links and PDH links, for example T1, E1, etc. Packet switching versus circuit switching. Advantages of packet switching over circuit switching. Most important advantage of packet switching over circuit switching is statistical multiplexing and therefore efficient bandwidth usage. No call setup for datagram switching. No per flow state information for datagram switching only. Simple to implement. Disadvantages of packet switching: potential congestion, packet delay, and high loss. Protocols needed for reliable data transfer, congestion control. Packet header overhead. Per packet processing overhead. T1/E1. Time division multiplexing allows a link to be utilized simultaneously by many users. The transmission is organized into frames. Each frame contains a fixed number of time slots. Each time slot is pre-assigned to a specific input link. If the buffer of an input link has no data, then its associated time slot is transmitted empty. A time slot dedicated to an input link repeats continuously frame after frame, thus forming a channel or a trunk. Pulse code modulation. TDM is used in telephony. Voice analog signals are digitized at the end office using pulse code modulation. A voice signal is sampled 8,000 times per sec, or every 125 emisec. It carries 8 bits at a time. The total bit rate of a time slot, as it continuously repeats frame after frame, is 64 kilobits per second. Examples of connections. Transmission on a T1 line is unidirectional, that is, data is routed from central office 1 to central office 2. For a bidirectional transmission between the two central offices, two separate T1 lines, each transmitting in the opposite direction, are needed. In order for subscriber A to talk to subscriber B, a connection has to be first established. This connection is set up by the telephone network when A picks up the receiver and dials the number for the called party. A signaling protocol is used to set up a connection that runs through the central offices that are along the path from subscriber A to subscriber B. The connection involves 1. A dedicated line from subscriber A to central office 1. 2. A time slot, for example time slot I, on the T1 line from central office 1 to central office 2. And 3. A dedicated subscriber line from central office 2 to subscriber B. In the opposite direction, it involves 1. A dedicated line from subscriber B to central office 2. 2. Time slot I on the T1 line from central office 2 to central office 1, and 3. A dedicated subscriber line from central office 1 to subscriber A. These resources are allocated to the phone call between subscriber A and subscriber B until one of them hangs up. A telephone connection is known as a circuit. Thus, the telephone network is a circuit switching network. The Digital Signal, DS, and ITU-T standard. It specifies how to multiplex several voice calls onto a single link. The DS standard is a North American standard, and it is not the same as the international hierarchy standardized by ITU-T. T-carrier/E carrier. The DS signal is carried over a carrier system known as the T carrier. T1 carries the DS1 signal, T2 carries the DS2 signal, etc. The ITU-T signal is carried over a carrier system known as the E carrier. The DS and ITU-T hierarchy is known as the Plesiochronous Digital Hierarchy, PDH. Plesian means nearly the same, and chronos means time in Greek. The North American hierarchy, the International ITU-T hierarchy, the DS1 signal, 24 8-bit time slots per frame. Each time slot carries 8 bits per 125 msec, or the channel carries a 64 kilobits per second voice, and one 1-bit time slot, slot F, for frame synchronization. On the F channel, the frame synchronization pattern 1010101 is transmitted. Some bits are used for signaling. T1/E1. T1. Total transmission rate, 24 by 8 plus 1 equals 193 bits per 125 memsec, or 1.544 megabits per second. E1. 30 voice time slots plus 2 time slots for synchronization and control. Total transmission rate, 32x8 equals sign 256 bits per 125 msec, or 2.048 megabits per second. Fractional T1/E1. Fractional T1 or E1 allows the use of only a fraction of the T1 or E1 capacity. For example, if n equals sign 2, then only 2 time slots are used per frame, which corresponds to a channel with total bandwidth of 128 kilobits per second. Unchannelized frame signal. The time slot boundaries are ignored by the sending and receiving equipment. In the unchannelized T1 frame signal, a L192 bits are used to transport data, followed by the 193rd framing bit. This approach permits more flexibility in transmitting at different rates. This scheme is implemented using proprietary solutions. The Synchronous Optical Network, SONET. SONET, proposed by Belcore, Telecordia. It was designed to multiplex DSN signals and transmit them optically. ITU-T adopted the Synchronous Digital Hierarchy, SDH, as the international standard. It enables the multiplexing of Level 3 ITU-T PDH signals, 34.368 megabits per second. STS-STMOC. The electrical side of the SONET signal is known as the Synchronous Transport Signal, STS. The electrical side of the SDH is known as the Synchronous Transport Module, STM. The optical side of a SONET/SDH signal is known as the Optical Carrier, OC. The SONET/SDH hierarchy, SONET/SDH. In SONET, a data rate is typically referred to by its optical level. In SDH, it is typically referred to by its electrical level. For instance, A 155.520 megabits per second data rate is referred to in SONET as OC3, whereas it is referred to in SDH as STM1. Not all levels are economically viable. Existing products, such as OC3/STM1, OC12/STM4, and OC48/STM16, are indicated by bold formatting. As can be seen, each level can be obtained from the previous one by multiplying it by 4. SONET/SDH is channelized. STS3 consists of 3 STS1 streams, and each STS1 consists of a number of DSN and E1 signals. STS12 is constructed by multiplexing 12 STS1 streams, and so on. In SDH, STM4 is constructed by multiplexing 4 STM1 basic rate streams. STM16 is constructed by multiplexing 16 STM1 streams, and so on. STM level for OCN is obtained by dividing n by 3. Concatenated structures, OC3C, OC12C, etc. The frame of the STS3 payload can be filled with IP packets. Concatenated SONET/SDH links can be used to interconnect IP routers, packets over SONET, after they have been encapsulated in PPP frames. The STS1 frame structure. The frame is presented in matrix form and it is transmitted row by row. Each cell in the matrix corresponds to a byte. The first 3 columns contain overheads. The remaining 87 columns carry the synchronous payload envelope, SPE, which consists of user data, and additional overheads referred to as the path overhead, POH. The selection, line, and path. Overheads. Section, a single link with a SONET device or a regenerator on either side of it. The section overhead, SOH, bytes, occupy the first 3 rows of the first 3 columns. It is associated with the transport of STS1 frames over a section. Line. A link between 2 SONET devices, which may include regenerators. The line overhead, LOH, bytes, occupy the bottom 6 rows of the first 3 columns. It is associated with the transport of SPEs over a line. Path. A path is an end-to-end connection between the point where the SPE originates and the point where it terminates. The path overhead, POH, is embedded in the SPE, and it occupies the first column. The SONET stack, the STS1 payload. The payload SPE consists of user data and the path overhead. User data, virtual tributaries, sub-rate synchronous data streams such as DS0, DS1, E1, and entire DS3 frames. IP packets. The STS3 frame structure, the channelized STS3 frame, is constructed by multiplexing byte-wise 3 channelized STS1 frames. As a result, byte 1, 4, 7 to 268 of the STS3 frame contains byte 1, 2, 3 to 90 of the first STS1 frame. Byte 2, 5, 8 to 269 of the STS3 frame contains byte 1, 2, 3 to 90 of the second STS1 frame. Byte 3, 6, 9 to 270 of the STS3 frame contains byte 1, 2, 3 to 90 of the third STS1 frame. This byte-wise multiplexing causes the columns of the 3 STS1 frames to be interleaved in the STS3 frame. The first 9 columns of the STS3 frame contain the overhead part, and the remaining columns contain the payload part. Error checking and some overhead bytes are for the entire STS3 frame, and they are only meaningful in the overhead bytes of the first STS1 frame. The corresponding overhead bytes in the other STS1 frames are ignored. STS3C, OC3C frame consists of 9 columns of overhead and 261 columns of payload. IP packets are packed into a single SPE. Higher levels of channelized STSN are constructed in the same manner as STS3 by multiplexing N STS1S SONET/SDH devices. Several different equipment exist: terminal multiplexer, TM, add/drop multiplexer, ADM, digital cross-connect, DCS, the terminal multiplexer, TM. It multiplexes a number of DSN or E1 signals into a single OCN signal. It consists of a controller, low-speed interfaces for DSN or E1 signals, an OCN interface, and a time slot interchanger, TSI. It works also as a demultiplexer. Add/drop multiplexer, ADM. It is a more complex version of the TM. It receives an OCN signal from which it can demultiplex and terminate, that is, drop any number of DSN or OCM signals, where M is less than N, while at the same time it can add new DSN and OCM signals into the OCN signal. SONET rings, SONET/SDH, ADM devices, are typically connected to form a SONET/SDH ring. SONET SDH rings are self-healing, that is, they can automatically recover from link failures. An example of a connection: A transmits a DS1 signal to TM1. TM1 transmits an OC3 signal to ADM1. ADM1 adds the OC3 signal into the STS12 payload and transmits it out to the next ADM. At ADM3, the DS1 signal belonging to A is dropped from the payload and transmitted with other signals to TM2. TM2 in turn demultiplexes the signals and transmits A's DS1 signal to B connection setup. Using network management procedures, the SONET network is provisioned appropriately. This is an example of a permanent connection. It remains up for a long time. The connection is dedicated to user A, whether the user transmits or not. A digital cross-connect, DCS. It is used to interconnect multiple SONET rings. It is connected to multiple incoming and outgoing OCN interfaces. It can drop and add any number of DSN and or OCM signals, and it can switch DSN and or OCM signals from an incoming interface to any outgoing one. SONET/SDH rings. SONET/SDH rings are typically deployed in a metropolitan area, either as metro edge rings or as metro core rings. A metro edge ring is used to transport traffic between customers and a hub, which is a SONET/SDH node that is attached to a metro core ring. Typical customers include ADSL-based access networks, cable-based access networks, small telephone switches, private branch exchange or PBX, storage access networks, SAN, and enterprise networks. A metro core ring interconnects metro edge rings, large telephone switches, and ISP points of presence, POP. It also sends and receives traffic to and from larger regional and long-haul networks. Metro core rings are interconnected using DCS nodes to form a mesh network. Self-healing SONET/SDH rings. SONET/SDH rings have been specially architected so that they are available 99.999% of the time. Average downtime for the network of only 6 minutes per year. Causes for ring failures: fiber link failure due to accidental cuts and transmitter/receiver failure. SONET/SDH device failure, rare. Automatic protection switching, APS. SONET/SDH rings are self-healing, that is, the ring's services can be automatically restored following a link failure or degradation in the network signal. This is done using the automatic protection switching, APS protocol. The time to restore the services has to be less than 50 memisec. Protection schemes, point-to-point, schemes for link protection. 1. Dedicated 1+1. 2. 1:1. 3. Shared 1:n. Working/protection fibers. In the 1+1 scheme, the two devices are connected with two different fibers. One is designated as a working fiber, and the other as a protection fiber. The SONET/SDH signal is split and then transmitted simultaneously over both fibers. The destination selects the best of the two signals based on their quality. If one fiber fails, the destination continues to receive the signal from the other fiber. In the 1:1 scheme, there are still two diversely routed fibers, a working fiber and a protection fiber. The signal is transmitted over the working fiber. If this fiber fails, then the source and destination both switch to the protection fiber. The 1:n scheme is a generalization of the 1:1 scheme, whereby n working fibers are protected by a single protection fiber. Since there is one protection fiber, only one working fiber can be protected at any time. Once a working fiber has been repaired, the signal is switched back, either automatically or manually, from the protection fiber to the working fiber. The working and protection fibers have to be diversely routed. That is, the two fibers use separate conduits and different physical routes. Often, for economic reasons, the two fibers use different conduits, but they use the same physical path. In this case, we say that they are structurally diverse. Classification of self-healing rings. Various ring architectures have been developed based on the following three features. 1. Number of fibers. Example, 2 or 4 fibers. 2. Direction of transmission. Example, unidirectional, bidirectional. 3. Line or path switching. Number of fibers. 2 or 4 fiber rings. 2 fiber ring fibers 1, 2, 3, and 4 are used to form the working ring, clockwise, and fibers 5, 6, 7, and 8 are used to form the protection ring, counterclockwise. In another variation of the 2-fiber ring, each set of fibers form a ring which can be both a working and a protection ring. In this case, the capacity of each fiber is divided into 2 equal parts, one for working traffic and the other for protection traffic. In a 4-fiber SONET/SDH ring, there are 2 working rings and 2 protection rings, one per working ring. As in the case of a point-to-point SONET/SDH fiber link, the working and protection rings are route diverse. That is, the fibers between 2 adjacent SONET/SDH devices use different conduits and different physical routes. The working and protection rings can also be structurally diverse, which is typically more economical. In this case, the fibers between 2 adjacent SONET/SDH devices use different conduits, but they follow the same physical path. Direction of transmission. Unidirectional ring. Signals are only transmitted in one direction of the ring. Bidirectional ring. Signals are transmitted in both directions. Line and path. Switching, path switching, restores the traffic on the paths affected by a link failure. A path is an end-to-end connection between the point where the SPE originates and the point where it terminates. Line switching. Restores all the traffic that passes through a failed link. Based on these 3 features, we have the following 2-fiber or 4-fiber possible ring architectures. Unidirectional line switched ring, ULSR. Bidirectional line switched ring, BLSR. Unidirectional path switched ring, UPSR. Bidirectional path switched ring, BPSR. Of these rings, the following 3 are used. 2-fiber unidirectional path switched ring, 2FUPSR. 2-fiber bidirectional line switched ring, 2FBLSR. 4-fiber bidirectional line switched ring, 4FBLSR. 2-fiber unidirectional path switched ring, 2FUPSR. Working ring consists of fibers 1, 2, 3, and 4, and the protection ring of fibers 5, 6, 7, and 8. Unidirectional transmission means that traffic is transmitted in the same direction. A transmits to B over fiber 1 of the working ring, and B transmits over fibers 2, 3, and 4 of the working ring. Used as a metro edge ring to interconnect PBX and access networks to a metro core ring. Typical transmission speeds are OC3/STM1 and OC12/STM4. The disadvantage of this ring architecture is that the maximum amount of traffic it can carry is equal to the traffic it can carry over a single fiber. Self-healing mechanism. Path-level protection using the 1+1 scheme. The signal transmitted by A is split into 2. One copy is transmitted over the working fiber 1, and the other copy is transmitted over the protection fibers 8, 7, and 6. During normal operation, B receives 2 identical signals from A and selects the one with the best quality. If fiber 1 fails, B will continue to receive A's signal over the protection path. The same applies if there is a node failure. 2-fiber bidirectional line. Switched ring, 2FBLSR. Used in metro core rings. Fibers 1, 2, 3, 4, 5, and 6 form a ring, call it ring 1, on which transmission is clockwise. Fibers 7, 8, 9, 10, 11, and 12 form another ring, call it ring 2, on which transmission is counterclockwise. Both rings 1 and 2 carry working and protection traffic. This is done by dividing the capacity of each fiber on ring 1 and 2 to two parts. One part is used to carry working traffic and the other protection traffic. A transmits to B over the working part of fibers 1 and 2 of ring 1, and B transmits to A over the working part of fibers 8 and 7 of ring 2. Self-healing mechanism. The ring provides line switching. If fiber 2 fails, then the traffic that goes over fiber 2 will be automatically switched to the protection part of ring 2. That is, all the traffic will be rerouted to ADM3 over the protection part of ring 2 using fibers 7, 12, 11, 10, and 9. From there, the traffic for each connection will continue on following the original path of the connection. 4-fiber bidirectional line. Switched ring, 4 FBLSR. 2 working rings and 2 protection rings. The 2 working rings transmit in opposite directions, and each is protected by a protection ring, which transmits in the same direction. The advantage of this 4-fiber ring is that it can suffer multiple failures and still function. In view of this, it is deployed by long-distance telephone companies in regional and national rings. Self-healing operation, span switching. If a working fiber fails, the working traffic will be transferred over its protection ring. This is known as span switching. Self-healing operation, ring switching. Often, the working and protection fibers are part of the same bundle of fibers. When the bundle is cut, the traffic will be switched to the protection fibers. This is known as ring switching. Data over SONET/SDH, DOS. The data over SONET/SDH, DOS network architecture provides a mechanism for the efficient transport of integrated data services. The following are some of the features of DOS. 1. It provides flexible bandwidth assignment with a 50 megabits per second granularity. 2. No modifications are required of the intermediate nodes. 3. Using GFP, it provides an efficient framing scheme with a small overhead. 4. It can accommodate IP packets, Ethernet frames, and constant bitrate data and control information carried by fiber channel. In particular, it provides an effective mechanism to transport GBE, which is widely deployed in wide area networks, WAN. 5. Coexistence of the traditional voice services and the new data services in the same SONET/SDH frame. 6. Network management through the SONET/SDH existing and quality-proven network management. DOS uses 3 technologies. 1. Generic framing procedure, GFP. 2. Virtual concatenation, and 3. Link capacity adjustment scheme, LCAS. These technologies have been standardized by ITU-T, generic framing procedure, GFP. GFP is a simple adaptation scheme that extends the ability of SONET/SDH to carrying different types of traffic. Specifically, it permits the transport of frame-oriented traffic, such as Ethernet and IP over PPP. GFP is the result of a joint standardization effort of ANSI Committee T1X1, 5 and ITU-T, and is described in ITU-T Recommendation G, 7041. 2 different types of GFP frames have been defined: GFP client frames and GFP control frames. Virtual concatenation. This procedure maps an incoming traffic stream into a number of individual subrate payloads. The subrate payloads are switched through the SONET/SDH network independently of each other. At the destination, they are used to reconstruct the original traffic stream. Example: let us consider the case of transporting the 1 GBE signal over SONET/SDH. According to the specifications, an STS-48C 2488 GBPs has to be used, thus leaving a lot of unused capacity. Using the virtual concatenation scheme, 7 independent STS-3C, 7x155,520 = 1088, can be employed to carry the 1 GBE signal at full rate. This works as follows. At the transmitter, the incoming stream is demultiplexed and distributed in some fashion over 7 different payloads, each an STS-3C. Intermediate SONET/SDH nodes, only see different payloads, and they are not aware of the concatenation. At the destination, the 7 flows get multiplexed into the single original GBE stream. Link Capacity Adjustment Scheme, LCAS. This scheme permits to dynamically adjust the number of subrate payloads allocated to a traffic stream whose transmission rate may vary over time. LCAS can be also used when rerouting traffic due to a failure.
The end of Session 1.